Thank you for watching Idealized Science Institute's long-form videos. Here, our goal is to help teachers teach purposefully. We have deliberately slowed down the process so teachers can dissect the lessons and find those hooks that will engage their students in authentic scientific practices. Now, these lessons are sequential, so please watch them in order. And if you like what we're doing, consider supporting the Idealized Science Institute. Visit our website where you could see other long-form videos, our podcast, we have quick quizzes, and so on. And as always, please put comments down below. And we are really hoping to hear from you as you enact some of these lessons in your classrooms. As you come back over, the students probably have already been manipulating the apparatus, and they are pretty certain about a claim. As they pulled on these, they said, now I really know for sure what's going on. Now on my board here, I'll have every student's name, and then I'll listen to what they're saying because I've been watching them brainstorm. And we'll say student 1 has made a claim, and his claim now, and I just put a little incrementation there, a little mark. I can keep track of every student, what they're doing. Said, I now know for sure what's going on. When I pull on these, I notice it's harder to pull on these. And so you'll ask them for the claim, and they'll say, as the number of pulleys, and you say, like, what do you mean number of pulleys? And they might say, the 3s or the 2s or the 1s. They would say, as the pulleys, and as a teacher, you might have to push on them and say, are you saying the pairs of pulleys? Is that what you mean when you say 3? And they'll say fine, or they might, tell you something different. Whatever it is, you want to have them really hash out their claim. And they will say, as the pulleys increases, the force would get easier that I have to pull. That would be read on our meter. I say, great. And they have that written out. But now you can take that to a higher level. You can say, can you make a graph as a claim? And often they're, going to be struck as that seems like an odd idea. You're basically asking me to tell you what the graph's going to look like, and that's exactly what you'd like to do. Have your students make a claim about what the graph is going to look like. And often they'll end up doing something like that. You can push them on this a little bit. Let's make a graph here. And they'll say, as our pulley pairs, I might go too low there. Let's just do this. Period. I'll put it right here. And they might end up saying force here, and they're going to be measuring in newtons. They've looked at the spring scale. And then they might say pulley pairs. They might end up saying, well, pulley pair here, pulley pair here, pulley pair here. From there, they might call this, let's say, 1 pulley. This is the 2nd pulley pair, and that is the 3rd pulley pair. So we'll call that pulley, and they were talking about pairs of them. And they're saying the force should go down. And so they might give a general idea of something like that. They might say, well, my claim is as the pulley pair number increases, it's going to get easier and easier. And so you can simply ask them to see if they can verify that. And they'll say, sure, I'm pretty confident in my claim. They can then take their spring scale and they can hold this up. And I'll put this on here. And that looks like about maybe 1 or 0.75. I'll put this on here and then I'll take a picture. And then looks like about 0.75 on there is what the students might say. and then they can hook it onto this one. Most of them will hold it. I'll have to hook these on to get a picture. And maybe that one's looking like about 1.5, something like that. And this one here, I'll hook it onto the second loop right here. And maybe that's like 2.5. Regardless, I'll take a picture of these and put them up there. So give me a minute. At some point, you have your students come back, and now they're going to discuss what they found. And right away, the students will say, no, we found this. This is true. And you'll say, how do I know it's true? And they'll say, well, we measured everything, and we found out that the numbers line up perfectly. Now, hopefully one of your students will say, what do you mean by lining up perfectly? The students will eventually get the hint and say, give us a minute, we'll be able to show you. So we'll give them a minute. The students come back, and now they're ready to present. They bring out their board, and they know that we've been skeptical. We know that they've been talking a lot, and now they want to show us that what they found is exactly what they thought. So they'll present their board. They'll put it right here. And you can see they've done a beautiful job here. Get out of the way. You can see along this axis you've got your force in newtons. Here you've got your pulley pairs, and they've even put their numbers, 2.75, 1.50, and 0.75. I think that's what I read when I was doing these. We took pictures, but we'll check. And you could see that looks like a nice straight line. If I were to take a meter stick, you could say, boy, that looks linear. The class is going to be impressed. And they've done a really nice job. Notice this is not the first time they've made a graph. They've got the axes labeled. They've got pulley pairs. That's the thing that they varied. And they're graphing on the y-axis what they measured in newtons. And everyone's excited. So certainly on my chart, I would put that they presented this to us. They took a leadership role, so presenting in front of the class is difficult, and we give the students points for that. Taking a leadership role, other students might ask them confirmatory questions, and we would increment them also. And this sounds like they've done a wonderful job, and they really have. However, when you look at this, you might ask the students, is this possible for this to be, as they're saying, a straight line? Let me mark that. And you might ask them, may I put a line on here? And maybe you don't need to put a line, but you can kind of see, if I were to make like a little dash line it best fits here. Going like that. What eventually happens when I end up hitting 3 pulley pairs is I start to decrease towards 0. What would happen if I had 4 pulley pairs? In other words, I could get another set of these pulleys. I could get a set of 4 on top and 4 on bottom. According to this, 4 pulley pairs looks like it would be dipping below 0. How can that be? And what if I went to 5 and 5? I would be way down in negative territory. What does that even mean? How can you have negative force? My scale would read backwards. It would go the other way, it would go up past 0 in the other direction. That shows us there's got to be some issue either in how we measured our logic, regardless, I don't think this claim can be true. So you want to give your students a little bit of time to grapple with that. Another group comes along and says, okay, we're not exactly sure, about the force with the pulleys, but we did something different that we would like to show. So, of course, we agree. Please, let us see what you've done. So they grab their board and they say, well, we ended up focusing on the distance and the distance that we pulled. And you could see that pulley pair 1, we pulled about 38 centimeters, where the second set of pulleys, the pulley pair 2, 75. And the third, 112. And the students aren't really convinced that they found anything. He says, I didn't have time to make the graph. We just figured this out as the other graph was presenting. He said, if I may, I'd like to graph it out. And we say, sure, go ahead. And he's going to do that on the main board here. So we're going to use these values right here. He's going to grab a meter stick and hopefully draw another one of these. Let's try and keep it equal, about 33-ish. Okay, so we'll put it right here. Okay, and then let's go up 7, 47, 54. Okay, good enough. And then I can go in this direction, and I'll do my, how far apart were these? About 10. So let's see if we can make this at the same 10, 20, 30. And we'll put little marks next to them, just to kind of keep them even. So he'll say that we're going to simply use that same idea, pulley pair 1, 2, and pulley pair 3. And now he's going to end up going up and down here, like this. Maybe he's going to make a graph, something like that. And he'll say, we're going to go up by 40s. And the rest of the class might be saying, why are you using 40s? These are really odd numbers. Shouldn't you do like 10, 20, 30, 40? He says, it doesn't really matter. So this student already has a pretty good idea of graphing 80 and then 120. And he says, if you don't mind, I'm going to plot my points. And he does. So at 1, we're at about 38. So put a little dot right there. At 2, he'll say 75, which is going to be a little bit below 80. And he's just trying to eyeball it the best that he can. And then 3 is 112, so that's going to be a little bit lower than our 120, something like probably about there. He says, you can see we have another linear relationship. Maybe we can make a little dotted line here, right? Let me put this on better. You can kind of make some dots here. And he'll make the dots a little bit bigger so we can see them, like that. Say, look, we now have our force, which is going down, and this one is going up. So he said, I think we found something rather interesting. Now, you always have that one student in the class. Maybe his father's the math teacher in the school, or, his brother was the star of math club or something like that. He suddenly says, wait a second, I see something really interesting. And often the other students can't follow along, but they're going to try. He says, may I approach the board? And you give him the board. And he says, wait, aren't we taking force times distance to get the work? And everyone's like, oh, we were supposed to do the work. We haven't really been solving for work. He said, actually, we have with our diagrams. He said, look at this graph here. If we were to multiply this line by this line, and maybe I'll make this into a line instead of a dash. See what this young man is positing. Maybe we don't need it all the way out here, so I can get rid of some of this. Wouldn't this times this, Now, a student in the back says, wait a second, you're about to multiply graphs? He says, graphs are just representations of our force and our distance. He said, I'm making a new claim. I'm making a claim that the work done, and remember, this is going to be our distance, and that's going to be in centimeters, is going to equal a graph that looks like this. So it tries its best to make it nice and neat. Let me just use the lines that I already have. He said, if this is our work graph, and that's 0, and this is going to be our pulley pair 1, 2, 3. He says, I don't exactly know what the work is, but he says, if I take a negative slope and multiply it by a positive slope, I would get no slope at all. And he posits, whatever the work is, it's going to be the same for all of these. The class would probably be flabbergasted at this point, but it's a really interesting way of thinking about having graphs multiplying together. It's a really interesting idea. So students are going to need to think about this for a minute. And as they are, he might say, look, these are each following our y equals mx plus b, as we already designated earlier. So this one's just a negative slope. And of course, it's not, we don't have the numbers here, we just have the trend. But it's an interesting idea. So you let your students think about this for a moment. And as a teacher, you should think about this also. Does a negative slope and a positive slope multiplied together give you 0 slope? That's a good question. As our students are grappling with the mathematics and science, which they're starting to understand are inextricably linked. You can't take your mathematical ideas and scientific ideas and pull them apart. They're intertwined, and necessarily so. And you might be thinking, my students aren't ready for this kind of thinking. And the real question is, why not? Yes, it's challenging. And of course, some of them are going to struggle, but they're probably putting things together that they never have before. And that's really what you're after. You're trying to change how they interact with nature and data, and maybe they've never collected data like this before. And getting the appropriate skepticism, getting excited about ideas while not being naive. So as they ponder, let them. And if you're thinking, my students might not be at this mathematical level yet, consider introducing some of those concepts now on the spot when they need it. It'll probably have much better stick than if you do it in some decontextualized form. As the students ponder the negative slope times a positive slope being no slope, doesn't seem to make a lot of sense, because a negative times a positive equals a negative, not a 0. But other students have said, look, these values here were never correct to begin with. This was just a trend. And if we really put the values there, which we should, and they were 2.75, 1.5, and 0.75. Let's go ahead and put those there. Again, we said they were 2.75, 1.5, and 0.75. Another student says, we got something similar, but that middle dot for 2 pulleys, we actually got 1.25. Let's just see what that is. Oh, wait, hold on. 1.25. So they said we got about here. Boy, that makes a huge difference right away. Notice that this looks linear right here. This looks linear. But this is starting to look a little bit like a curve. Something like that. And that's really the problem here, we think. When we look back at the pictures, I also got a slightly smaller value here. I think the problem is in our spring scales. This spring scale goes up to 20, but we're only going to our maximum of not even 3, which is all the way up here. When we grab the other spring scale, it goes from 0 to 5. So this would be 1, 2, 3. So we're going to be able to see our values with much greater precision than with our other spring scale that goes to 20. So we're going to recollect very quickly using that scale. I'll just take some pictures. Now that I have our new values, we're going to put those in. We have 2.4, 1.3, 0.9. 2.4 up 1, there's 2.5, 2.4 is about right there. 1.3, there's 1.25, it's about 1.3, and then 0.9 would be right here. That doesn't look linear anymore. That looks like it's curving down something like this. Curving. The students need to figure out the next step here, though. Now it feels like we're getting somewhere with this curve, but pulley pairs, that's interesting. It'd be neat if we could find numbers that were in between a pair of 3 and a pair of 2. In other words, are there other configurations? So here I have 1 and another pulley. Here I have 2 and 2, and here I have 3 and 3. Are there pulleys that are between those? In other words, do I have more data points that I could put in here? We're going to let the students ponder that. As your students are pondering if different configurations of pulleys are possible, let's understand that every teacher is going to be in a different situation. You can have a different classroom environment, different groups of students, different ages. All of these decisions need to be made by the teacher, and whatever suits your needs. Let's picture that you don't have a block schedule that's, a double period. Let's say you only have single periods. None of this would fit into a single period. None of it would fit into a block. You need to think about how much time you're willing to devote. Is it worth it? And I'll tell you it is. And if not, if you can't fit the whole thing in, what pieces do you fit in? All of these decisions are going to influence how your year goes. So if you can kind of think ahead, but back to the pulley situation. If you have pulleys that are already set up, students will realize that I could have a single pulley up top. But it really gets confusing when you say, okay, what's in between just one pulley, and then you have a pulley on the bottom, and then you have 2 pulleys, a pulley here and a pulley here. Can I have 1 and 2 or 2 and 1? These are things that you need to figure out if you want your students to engage with. It might also be worth having them set up one of these configurations. Everything looks easy till you try it. So you need to make those decisions. As we go back over, we'll probably find that our students have already thought of this. So let's go see what they're up to.